It is one of the strongest and most reliable materials we use today. A true modern titan, capable of withstanding wind gusts equivalent to a Category 5 hurricane without losing its stability or compromising its structure. In the United States alone, more than 200 million sheets of plywood are produced every year. A colossal figure that requires transforming entire logs, sometimes more than a meter in diameter, into incredibly thin, uniform, and surprisingly strong layers. But here the great question arises. How is it possible that a tree, with its natural fibers and seemingly fragile appearance, ends up becoming one of the strongest and at the same time lightest materials in modern industry? What happens inside a factory that allows a raw log, freshly fallen from the forest, to become a shield capable of facing forces that rival the fury of nature? In this video, we will explore the fascinating journey of plywood, a material that combines lightness with an astonishing ability to absorb violent impacts, especially those caused by debris flying at high speed during severe storms. This quality allows it to prevent window fractures, reinforce vulnerable walls, and protect entire structures from damage that would otherwise be devastating. Plywood acts as a kind of natural and intelligent shield. It withstands wind, repels moisture, reduces the effects of intense vibrations, and can bear the demands of extremely aggressive tropical storms without giving in. Its secret does not lie in a single material or special treatment, but in its internal design. It is made of several thin layers of wood called veneers, placed one on top of another, each with its grain oriented in the opposite direction of the previous one. This brilliant, almost architectural strategy creates a panel that distributes stresses evenly and resists bending, impact, and pressures that would destroy an ordinary solid board. Unlike a solid piece of wood that over time can warp, twist, crack, or lose stability, plywood is specifically manufactured to withstand extreme conditions without deforming. Its multi-layer structure gives it exceptional dimensional stability, making it an indispensable ally in contemporary construction, as well as in the manufacture of furniture, boats, decorations, and countless products that require strength without excessive weight. However, reaching the point where this material became so accessible and common was not an easy path. For centuries, its production was limited and expensive. Mass manufacturing only became viable in the 19th century, when the Industrial Revolution introduced technologies capable of producing it precisely, quickly, and economically. Creating a lightweight and inexpensive material that was nonetheless strong enough to compete with metals such as steel was a monumental challenge that required innovation and a deep understanding of the structure of wood. Curiously, this technological advancement was inspired by ancient techniques. Civilizations like the Egyptians, more than 5,000 years ago, already joined thin wooden sheets to make stronger furniture. Centuries later, modern engineers took that ancestral idea and perfected it. They developed methods for laminating extremely thin layers with near-surgical precision, controlling the orientation of each fiber. This is how the modern plywood system was born, a brilliant solution to amplify the natural properties of wood. In its early years, the process was slow, laborious, and far too expensive for widespread industrial use. But everything changed with the arrival of rotary lathes, machines capable of transforming an entire log into a continuous ribbon of wood as thin as a sheet of paper. Alongside this, the appearance of much stronger synthetic adhesives revolutionized the industry. Veneers could be bonded with tremendous firmness, creating panels that would not separate or give way under pressure. These advancements turned plywood into one of the most versatile, economical, and resistant materials of the modern world. It was the first major wood-derived product to be globally recognized for its stability, durability, and surprising load-bearing capacity. In fact, a properly manufactured panel can be stronger than a solid board of the same thickness. Its structural performance depends directly on the orientation and sequence of its layers. Each veneer positioned perpendicular to the previous one increases rigidity, reduces deformation, and distributes internal stresses with extraordinary efficiency. Today, companies such as Productos Colombia Forest operate highly specialized factories, like the plant located in North Carolina. There, 5 days a week, machines work almost non-stop to produce about 12,000 panels per day. Most are destined for construction projects: walls, roofs, furniture, and formwork. The rest is used as a protection system to reduce damage caused by hurricanes and extreme weather events, becoming the first line of defense for hundreds of communities. The factory mainly uses high-quality poplar trees, especially yellow poplar, a species that can reach impressive heights in the forests of the southern Appalachians. Its rapid growth ensures a constant supply, while its straight, uniform, low-density trunks are ideal for producing veneers without imperfections. Although classified as a hardwood, poplar has a less dense cellular structure than other species, which allows it to be peeled almost as if it were a piece of fruit. Forestry crews carefully select mature trees between 20 and 30 meters tall, as straight as possible and with few knots, since these characteristics determine the uniformity, strength, and quality of the final sheets. The logging is carried out with high-precision machinery capable of cutting, felling, and processing each tree in a matter of minutes. After cutting, the logs are divided into sections called bolts, which are then loaded onto trucks and transported to the plant. Once there, they are cut again with industrial chainsaws, adjusting their length to match the final dimensions of the panel. This step not only makes the material easier to handle, but also allows the logs to be obtained with grain oriented in specific directions, a crucial detail for producing reinforced plywood through the crossing of fibers. After the logging, the trunks begin a journey that seems taken from a perfectly synchronized mechanical choreography. They first move toward a set of rotating blades that remove the bark with surgical precision. This process is almost hypnotic. The blades spin at high speed and lift the bark layer by layer, as if they were stripping the tree of its external armor. In a matter of seconds, what was once a rough surface full of irregularities becomes a polished, smooth cylinder, completely clean and ready for the next step. Once stripped of their bark, the logs move directly to the machine responsible for peeling them, a colossal industrial lathe that looks more like a futuristic engineering instrument than a carpentry tool. Every day, nearly 3,600 log sections, each about 2.5 meters long, reach these blades. This amounts to almost 190 pieces per hour coming into contact with the system, a constant flow of wood that keeps the machine working without rest. And what happens at that moment is simply impressive. The enormous and powerful lathes begin to rotate the log with an almost hypnotic force. At the same time, a steel blade, sharp as a razor and nearly a meter long, slides toward the surface of the log. The machine removes about 14 meters of wood per minute, slowly transforming the solid log into a continuous ribbon of wood. It is like watching a colossal pencil sharpener take an entire log and unroll it into perfect spirals. From this mechanism, the veneer is born, the fundamental component of plywood. In a matter of seconds, a log that weighed hundreds of kilos is reduced to a thin, incredibly uniform strip just 1.6 millimeters thick, yet capable of reaching up to 30 meters in length. This strip is so flexible and continuous that it behaves almost like a giant sheet of freshly printed paper. To maintain the peeling quality, the blades must be replaced approximately every hour. Even the slightest loss of sharpness could compromise the uniformity of the veneers. That is why specialized technicians visually inspect the blades and adjust their cutting depth with micrometers that allow variations of less than 1/10 of a millimeter. After peeling, the continuous ribbon is cut into more manageable pieces, generally 1.37 meters wide and 2.5 meters long. These dimensions are not random. They correspond to standardized measurements that facilitate later assembly and allow material optimization in construction processes. However, there is an important challenge. Freshly cut poplar retains a high moisture content, which makes it easier to peel. But that same moisture can deform the wood if not controlled properly. To prevent any issues, the newly produced veneers are immediately fed into a massive industrial oven known as a roller dryer. This dryer is comparable in length to a full football field. Inside, the veneers move along rollers while streams of hot air, at temperatures close to 150 degrees Celsius, quickly remove the excess moisture. The goal is to reduce the moisture content to around 8%, the ideal point to ensure the wood does not warp during gluing or during the panel's lifespan. The trip through the dryer lasts only a few minutes, but it is essential for stabilizing the material. When the veneers emerge from the opposite end of the dryer, they are completely dry, flat, and ready for a rigorous inspection. Here they are classified according to their quality. Technicians look for knots, cracks, weakened areas, or color variations. Perfect veneers are destined for the outer layers. Medium quality sheets, or those with small defects, are used in the inner core, where they will be protected by the upper layers. After classification, one of the most important moments in the process arrives: the assembly. A machine applies an extremely strong industrial adhesive to the veneers that will form the core of the panel. This glue is not applied randomly. It is distributed using an automatic nozzle system that guarantees exactly the same amount and pattern on every sheet. Uneven application could create air pockets or weak points, so precision here is essential. One by one, the veneers are stacked in multiple successive layers. Each sheet is oriented perpendicular to the previous one, creating a cross-laminated core. This alternating orientation of the grain is the heart of plywood design. Thanks to this crossed pattern, the final panel becomes incredibly stable and resistant, preventing it from warping, bending, or cracking over time, even under heavy loads or abrupt changes in humidity. Once the veneer sandwich is assembled, the entire set moves into a gigantic high-temperature hydraulic press. Here, one of the most decisive processes takes place: hot pressing. The press reaches temperatures close to 124 degrees Celsius, while simultaneously applying enormous pressure that compacts all the layers. Depending on the type of panel and its final thickness, pressing lasts between 5 and 20 minutes. During this process, the heat activates the adhesive, while the pressure expels any air bubbles trapped between the veneers. When the cycle ends, all layers have become a single, rigid, compact, perfectly uniform, and surprisingly strong panel. When leaving the press, the panel is still hot. It needs a brief rest for its temperature to drop and its fibers to stabilize. Then it moves to the final stage: cutting, calibrating, and sanding. The excess edges are removed with laser-guided saws that ensure measurements accurate to the millimeter. Afterwards, each paddle passes through automatic sanders that leave its surface smooth and ready for any later application. Finally comes the visual inspection. Specialists examine each panel centimeter by centimeter, looking for imperfections, small bubbles, irregular lines, thickness variations, or microscopic cracks. Only the panels that pass this test are considered suitable for structural applications. The natural wood grain not only provides visual beauty, it is also a key component of the panel's strength. And this leads us to an inevitable question. How strong can a plywood panel really be? To answer it, in specialized laboratories in the state of Oregon, panels are subjected to extreme tests. Testing equipment applies forces that simulate real and even more severe conditions. They compress them, twist them, bend them, and literally force them to fail. This allows experts to determine exactly how much force a panel can withstand before breaking. The results are astonishing. When used in walls or structural reinforcements, these panels can withstand winds equivalent to a Category 5 hurricane. In the most extreme tests, the wood only yields when winds close to 800 kilometers per hour are simulated, a force greater than any storm ever recorded in the planet's history. And yet, the most fascinating part of all is that the basis of this modern technology comes from a principle humans were already using more than 5,000 years ago. An ancient legacy that today supports skyscrapers, protects homes, and forms part of some of the most important structures in the world.